Hi class, we are now on chapter 20.7. We're going to be discussing batteries and the chemistry used to generate electricity. So the first thing we're going to talk about is dry cells. And dry cells, so uh, instead of discussing dry cells, let me take a step back. We're going to, as we go on with this section, we're going to discuss lead storage batteries and other voltaic cells. These cells have aqueous electrolyte solutions or salt bridge that connect the half cells. But the cells that are used in electronic appliances are dry cells, which contain mobile ions in a paste or a gel. And what these are, they're considered dry compared to the way other cells are used or can put together. So we're going to look at a common dry cell and an alkaline dry cell. Now, the key thing about these, they are not rechargeable. Um, there are rechargeable dry cells, however, these are not, the ones that we're going to first look at are not rechargeable. So if we look at this half cell reaction here, we have at the anode, we have zinc that gets oxidized. And then at the cathode, we have manganese, excuse me, manganese 4 oxide, ammonium, and so I can explain how this is if we look at this here. We have a cell voltage of 1.5 volts. Here we have two terminals. We have the positive and the negative. We have the zinc case, which is the anode. We have a moist paste made of manganese 4 oxide and ammonium chloride. And then we have the graphite rod, which is the cathode. Okay, so if we look at this here, excuse me, with the dry cell, we have it consists of a small zinc case that acts as an anode, and inside, excuse me, inside the zinc is a layer of coated paper surrounding an acidic paste containing manganese 4 plus the ammonium chloride, with a carbon rod down the middle to act as a cathode. Now we're going to look at alkaline. I'm going to jump over to, this is all the same stuff, but I'll come back to it. The alkaline dry cell is simply that the alkaline involves zinc as the anode, same, and manganese 4 oxide as the cathode. But the difference is that it has a basic electric paste. And you can see here, which is the potassium hydroxide. So that's just one of the differences in it, is that makes it alkaline is because it has a base in it compared to the simple, if you want to call it a simple dry cell. So if we take a step back, excuse me, write a balanced equation for the cell. So a simple zinc dry cell. So if we pull out this information, what would be at the anode, what would be at the cathode, and the overall, remember we would balance these out with the electrons and so forth, and then we would have our overall balanced equation for this. Okay, what is the half cell potential for the cathode? So we find the standard potential. Remember, we have a table, and this is from another book, so it's not going to be Appendix A5 most likely. We pull our information, and what we can do is we know that a simple dry cell is 1.5 volts. You see the cells? So we isolate the cathode, and we can determine what the volts are at the cathode. Okay, so here is, if you look, it's pretty much very identical, except for the fact that it is in a potassium hydroxide paste. That's the only difference, and the cell voltage is 1.54. So it's a little bit longer, so that's where it says longer shelf life than the acidic dry cells, longer working, and little corrosion of zinc. So it's a little bit better, you know, depending on compared to what the simple dry cell is, but still. These are not rechargeable, so that's the downside on this. And here's again another picture. You can see the paste of the magnesium 4 oxide, potassium hydroxide, and the graphite powder. Okay, so then we get to the lead storage battery. So with the lead storage battery, and I'll show a picture of this, it is a car battery that's made up of six lead storage cells linked in a series. So these are up against each other. And each lead storage cell consists of a lead electrode coated with a paste of lead 2 sulfate. Excuse me, and another electrode that has lead 4 oxide as the active oxidizing agent. Excuse me, again, I don't know why every time I record, my voice starts acting up. It's also coated with lead 2 sulfate. The electrolyte is concentrated sulfuric acid, in which the lead 2 sulfate is insoluble. Both these electrodes are placed in the same solution, so they're in the sulfuric acid. And if we look, we can look at what the reactions are here, where the oxidation takes place and the reduction takes place. So if we look here, we can see that this here, the sulfate ion and the 4 protons, these in this equations, these are due to the concentrated sulfuric acid. As the discharge reaction proceeds, so as this keeps going, the sulfuric acid, which is made up of this and this, is consumed, and water is produced, which is what you see on this side. Okay, so this just says the same. 6 electrochemical cells in a series. You can see that's kind of showing some of what's inside here. Producing 2 volts for a total of 12 volts. We have an electrolyte that's 30% sulfuric acid. And now, as I understand them, these are actually sealed devices to prevent injuries from the sulfuric acid. Obviously, we don't want to have anything like that, on us. Again, you can see more pictures of an example of what the electrodes being submerged in the same solution. Okay, so calculate the potential of a single cell. So we know that these have 6 lead cell storage cells. What if we want to know 1? So we can pull our information from the appendix. We have our information for the anode, information for the cathode, and of course then we can set this up, and it gives us the cell potential for a single cell, excuse me, is 2.0501 volts. And the second question here is calculate the total potential of the 6 cells. Is it really a 12-volt battery? So here is now just dimensional analysis in itself. We know we have a total of 6 cells. We have for one cell the voltage, and if we handle this and set it up with stoichiometry, the total is 12.300 volts. So it has actually slightly higher than 12 volts, but that's what based on this calculation. Okay, so recharging a lead storage battery. So recharging a lead storage battery. The car battery recharges as you drive the car. The alternator sends electricity through the lead storage battery in the reverse direction. And this external source of electricity, it forces the excuse me, I lost my thought. Forces the chemical reactions of the lead storage cell to go in the reverse direction. This ends up regenerating the original reactants. So if we can go to here, we are now showing what happens as we're recharging the lead storage battery. So it's proceeding. These are the reactions that allow this to happen. So when the battery is recharged, the cathode and the anode are switched. That electron flow in electrochemical, it's okay. So when the battery is recharged, I think I said this, the cathode and the anode are actually switched in this case because the electron flow in an electrochemical cell is always from for this type is an anode to a cathode. So the flow of electrons is reversed because of the external source electricity. So the electrons are also in a sense reversed because it's always the electron goes from an anode to a cathode. And since we were recharging this, it's reversing it into this. So reduction always occurs at the cathode, oxidation always occurs at the anode. And because we're reversing it, the electrodes have become reversed in order to have this happen. So now we're going to look at another rechargeable battery, and a nickel cadmium is a common storage battery, and what it does is it consists of it's a voltaic cell, consists of an anode of cadmium. I know I'm not saying that right, even though I've worked with this stuff, and a cathode of hydrated nickel oxide. The electrolyte is potassium hydroxide in this case, which is not, I don't see it even listed here as that. So these were the batteries that were first widely used, rechargeable batteries for consumer devices. I remember this actually. I know this because I used to charge one of these and I used to read that. It used to say that. Probably still does on some of the batteries. So these were used in calculators, portable power tools, shavers, toothbrushes. And as you can see here, these half reactions are reversed when the cell is recharged. So these actually have a number of advantages as rechargeable batteries, but they do have one major disadvantage, and I saw it the minute I know because I've worked with this chemical, and that's cadmium. Cadmium is very toxic. So that is a big problem with this, and it's highly toxic to most life. Even, you can't even dispose of it without precautions because it's a huge environmental hazard. So governments actually limit there's a strict limit on using this substance because of how toxic it is. So because of that, obviously they've looked at other alternatives. So if we look here, we have a nickel metal hydride. So there's a nickel, M for metal, and a hydride. And this is a good substitute for the nickel cadmium batteries because it retains most of the advantages. Instead of cadmium, because cadmium's very, very toxic, these use a metal alloy hydride for the anode. But they actually have the same cathode as the nickel cadmium batteries. So they actually have the similar capacity as the other ones. However, these are lighter batteries and they're less harmful to the environment. So this is actually a plus thing compared to how much damaging the cadmium batteries can be. Lithium. So now we'll look at a lithium battery, and lithium batteries are very popular for portable devices. They have two advantages over the nickel hydride. They are lower weight for given output and higher voltage. So when we look at lithium, these are also they're the newest, but they're also the most expensive of, excuse me, the rechargeable batteries. This is the least dense metal. So that means if you think about how dense something is, I think of thickness. This is the least of the thickness of them. So it's a lot lighter, but they also have high energy density. So what that means is that, think about gas. If you put gas in your car, you want, they're saying more bang for the buck. So you want to put a gas that's going to give you more energy. So you're going to go more miles with a certain gas compared to a cheaper gas, maybe. So you want to get as much out of it as you can. And that's what greater energy density is that it has more energy in it compared to something that's approximately the same size. So it'll give you more power. It'll last longer than something else. So that's what greater energy density means. So these batteries actually also work different than other batteries. Your book goes into it a little bit, and pretty much what it says is that the flow of the anion, you know what, hold on a second. It's interesting because your book says that the details of the operation are beyond the scope of this current discussion. So it doesn't go into it too much. But what the key thing is that this primarily follows the motion of the lithium ions from the anode to the cathode. And when it's in reverse, the flow of the lithium ions from the anode to the cathode causes a corresponding flow to the external circuit. And that's not the part I was looking at. Sorry. I was looking at a part to highlight here and I lost it. So here it is. So your book says that it's beyond the scope, but when it is, so these are rechargeable. So the key thing is to remember that they're rechargeable. So what happens is that when upon discharge, the lithium ions spontaneously migrate to the cathode, which consists of a lithium transition metal oxide. That transition metal is reduced during the process. Upon recharging, that transition metal is oxidized, forcing the lithium to migrate back to the graphite. So that's what you're seeing here, is it's forcing it back in. So it will leave this and go through, and then when it's being charged back, it will force that back into the graphite, and it will keep repeating itself. So it'll go one way, and then it'll go the other way, is what I'm trying to point out here. So energy density, remember, this is the more bang for the buck. And what this is that you can see that some of these, it has the highest energy density. So if you think of this in terms of gasoline and mileage, you want the gasoline that's going to give you, when it combusts, that's what helps move the pistons. So you want something that's going to combust a lot longer, go longer. That means more miles. You can get more out of it. And that's the same as these. So the higher these values are, that is the amount of potential energy that can be used a lot more than some of the other ones that you see here. Okay, so fuel cells. Sorry. Okay, so now we're going to discuss fuel cells. And up until this point, we've actually, though I haven't really stated it, that we've been dealing with we've been dealing with closed systems. So there's a certain finite amount of reactants and products, and finite concentrations is what I should say. And eventually it will decline and it'll be depleted, and it'll decrease, and then it will be zero. It'll eventually, that's it. It's done. However, we're going to look at a certain type that doesn't happen to, and that's what this fuel cell is. It generates a continuous flow of electricity. So with these, so when we're dealing with this type of fuel cell, it generates a continuous flow of electricity. However, It needs to have an ongoing supply of reactants, fuels, and also a way of dispersing the resulting products. So we're going to take a look at this now. So the most common of the fuel cells is hydrogen, which reacts with oxygen, and it gives off an explosive reaction, and that releases a good deal of energy, which is what we want. We want that energy. So because of that energy, you want to separate this to get the electrons to flow and to be able to use this electrical work. So so basically that the energy can be released in a more controlled and useful way. So electrical energy. So at the anode, here's what anode. Hydrogen gas is oxidized, so we end up generating protons and electrons as per the standard hydrogen electrode, which is, remember, SHE. The electrons flow to the cathode, so they flow this way. And while the cathode, so the protons travel through the electrolyte to the cathode, where they combine with oxygen and the released electrons to form water molecules. So what we do is that we can combine this and we can get a direct, to understand the overall. So let me see, this is the cathode reaction, this is the anode. I thought I had the overall reaction here, which is right here. So we see it as two half reactions, but here is the overall reaction to it, which is a direct reaction of two gases. So I try to, here's the oxidation, here's the reduction. I try to make it bigger so you can actually see what's going on here. And this slide is pretty much saying exactly what I just stated and how the process works. Okay, and then again, here's another, it kind of shows you the hydrogen and the electrons that go, the electrolyte, depending on what kind of hydrogen fuel cell it is. So let me explain this picture. This is a diagram that shows the continuous input of hydrogen. So you see the hydrogen here, and atmospheric oxygen. So that's just open to the air. And the continuous output of water. So the water leaves. So this is where this has to, in order for this to go, we have to have a supply of reactants and a place to allow the products to go. So the hydrogen gas is oxidized as it passes over the catalytic surface in this case. So it's going to, when it comes into contact with this, oxygen gas is reduced. You see how it goes across the electrolyte. So the ions go across the electrolyte, the electrons go through the external circuit, and then this comes into contact with oxygen, and the water is produced as it, since the oxygen gas is reduced by the electrons from the hydrogen, and forms water, and then the water is given an output to be released. Hopefully that makes sense here. Okay, so what is the standard potential of a hydrogen fuel cell? Well, we're dealing with two gases. We're dealing with hydrogen and we're dealing with oxygen. So one is at the anode, and it's the standard hydrogen electrode, the SHE. And then we're dealing with oxygen. So we can plug these in. Remember, it's with the zero value. So the standard potential of the hydrogen cell is 1.23 volts. And review dry cell and lead storage cells are voltaic cells commonly used in batteries. The reactions of some voltaic cells are readily reversible, but not all of them are, making it possible to recharge them by applying an outside source. Some of these, such as cadmium, use of cadmium is very toxic, so there are other types of rechargeable batteries that are chosen over those because of how toxic they are to the environment. Fuel cells are voltaic cells with a continuous input of reactants. So in this case, we would need a continuous input of hydrogen and oxygen. And we would also need an outflow for the products, this case being water.